Hello, hello. Welcome to the UESI Lunch and Learn. My name is Rihanna, and I'm the new Marketing Communications Coordinator for UESI. Awesome. I'll be moderating this webinar today and just want to let you know we will have a Q&A. Sorry if I'm looking everywhere. We will have a Q&A portion at the end of this webinar. So while you are welcome to post your questions in the chat, we ask that you wait until the end of presentation for answers. So I will now introduce our speakers, Phil Martin and Jim O'Dowd. Phil Martin is the gentleman on the right. Jim O'Dowd is the gentleman on the left. So Phil Martin is a professional engineer and land surveyor with over 37 years of experience in land development, waste and wastewater transmission and treatment, and utility management. Mr. Martin is the Executive Director of Augusta Water, which provides water and wastewater services to the residents of Augusta County, Virginia. He holds a bachelor's degree in civil engineering technology from Bluefield State College in Bluefield, West Virginia. He is a member of the American Waterworks Association, Virginia Rural Water Association, and currently serves on the ASCE Utility Asset Management Division's Practical Data Analysis Committee. So prolific, I love it. Meanwhile, we have Jim O'Dowd, a professional engineer with over 29 years of experience in water and wastewater consulting. He was the infrastructure asset manager with the Western Virginia Water Authority in Roanoke, Virginia for a decade, and has been working with AECOM for over 6 years. He holds a bachelor's degree in civil engineering from University College in Cork, Ireland, and Mr. O'Dowd is the current chair of the ASCE Utility Asset Management Division's Practical Data Analysis Committee. He has presented papers at national and international conferences with a primary focus on hydraulic modeling and asset management. Please join me in welcoming them both here, and thank you both for being here today. We're excited to learn more from you.
Great, thanks. Just some housekeeping here. First off, can you see the screen I'm sharing?
Yes, I can.
Okay, now hopefully it's the right one, is it?
I mean, it has your face and your bio. If that's what you're trying to share, then yes.
Okay, right, and I'm actually going to stop the video and because for bandwidth issues here, and I will keep going. Bear with me 1 second. All right. Okay, so thanks everyone for joining us today. So the learning outcomes of this session are going to be initially like learning the basic principles of an asset register, understanding the basics of GIS, looking at the relationship between inspection and asset data, looking at what data to mine from interventions, learning new ways to visualize that data. And of course, the big thing is you've got a lot of data, but how do you convey information? What's going to be useful to stakeholders? So we'll be talking about that, and also looking at various tools we can use to inform the asset register. So topics of discussion will be the purpose and background, a little bit of history and what we're doing here, then get into the basic principles of the asset register, look at available mapping data, get into GIS, and look at updating that register from incident data, intervention data, and inspection data. And then also we'll get a utility perspective from my good friend Phil here. Okay, so this is the fourth presentation from the committee that Phil and I started there about 5 or 6 years ago. It's part of the UESI's asset management division. So we've been doing these kind of annually now, like in December each year. So, and what we're trying to do is, there's lots of conferences on throughout the year, and a lot of people may not actually make it to those conferences, and so a lot of the material can be at times challenging. So we try and break it down to be fairly simple, to show how like any utility can address inventory issues or any other data challenges. So this water one is the first water one we've done. We've done 3 sewer ones already, but it's going to lay the groundwork for future webinars we're going to be presenting. And we'll be talking about the most important components recommended to be captured in the asset register, and also the related technologies and tools. So this is a matrix here showing the goals and challenges of any utility, be it small or large. and then also the activities and data sources for answering and addressing those challenges. So the one here on the far left is the first one we're doing is the basis of everything, right? So it's preparation and efficient updating of the asset register, and be on the lookout in the next couple of years for other ones on, optimization of renewal and maintenance processes and water loss and all sorts of things. So what's an asset register? So it's a detailed listing of assets owned by a utility, recording multiple characteristics of the assets. It stores valuable data like physical, financial, and operational parameters to facilitate informed and defensible decision-making and analysis. And one of the most important things is having a unique identifier for each asset. We don't want to see its, pipe at the intersection of Main Street and Elm Street. We'd rather see it be, pipe ABC. And then, but it grows from there to include, status, history, condition, and performance. So mapping is absolutely integral to this for utilities because it tells us where the assets are located. And you might have heard the term of asset registers for businesses, because it contains like detailed purchase history. But because of the age of infrastructure in this country, where it can date back to the 1800s, we a lot of times have to estimate the original asset costs, depreciation, and present value. So we're going to talk about the available asset register data from as-built down to GIS here. So as-built are record drawings. They can date back, maybe even 150 years. And you'll see something like this, right? And then maybe in this, I don't know, the 60s or 70s, you might have seen like section maps, and those would be inked. And then we graduated to CAD drawings then, probably in the 80s and 90s. And those would be replacing the inked ones. And then we get to like modern day, which is the GIS. And just a note on this network here, I know some eagle eyes might see this is saying Blacksburg, Virginia, and there's Virginia Tech, and I'm actually right here. I live here. This is not the town of Blacksburg's water system. It's just a dummy system that we built a couple of years ago for illustrative purposes. So just to let you know about that. So what's in the GIS, right? So for water, we're saying the usual suspects, right? We've got the mainline pipes here. We've got service lines. We've got meters. We've got fittings, like T's or bends, whatever. We've got hydrants and valves, right? And what we're doing in this presentation, similar to the sewer ones we've done in the past, is we've divided up the data from like bronze, silver, gold, and platinum. So and we're do it sequentially in that order, right? So if you're starting off, we get bronze data. What do we consider that to be? So it's pretty similar across the asset types. For pipes, valves, hydrants, and meters. So for pipes, diameter, material, year installed, and operational status. And it's quite similar for the other asset types. For pump stations, tanks, and reservoirs, we'd be looking for the, or water treatment plant sources too. We'd be looking for the location, year installed, operational status. And what does that tell us? So we're looking at that little area again here. So, on the pipe here, we've got, it's a mainline pipe. Diameter is 8-inch. Its material is spun iron. It was installed in 1925, and it's an in-use pipe. It's not abandoned or proposed or anything like that. There's a hydrant here, installed in 1924. It's in use, and the valve, 8-inch, 1922, right? Very basic data. And then you might have tank information. So we've got this north elevated tank here, and that might be all you have, right? There's a pipe connected to it, and that's about it. And then also you might have a pump station here. And again, you just know where it is. And that is all you would put in your mapping. So once we have that information in the GIS and in a field, you can then theme that information. So we're going to look at a few of those, but you can theme anything's in a field that can be themed, right? So we've got pipe diameter, pipe material, asset age, operational status would just be some choices. So to illustrate that, on the pipe diameter here. Like these pink pipes are 6-inch, these 8-inch pipes are blue, 12-inch pipes are green, and we've got the 24-inch pipes here are brown, right? So then you know that, okay, this blue one over here, that's an 8-inch, right? Pretty easy. And then pipe material becomes really important down the road. But so we can see here in brown here, we've got cast iron pipes. So that's where, you know, the town started. And then we've got spun iron here in orange. And then we got a water treatment plant over here. And then as the system grew, you know, we've got some galvanized iron here. That was an experimentation with that. We got some ductile iron here in blue. We got PVC is green. So you can kind of see how the more modern pipe is on the outskirts of the town there. Okay. So the outcome of having that data, so the data is very basic, but it's fundamental. And it allows for simple understanding of the system, and it sets the stage for the next level of analysis. So if you're transitioning from nothing to bronze, you can digitize paper maps and record drawings, use standards for choice lists, really important. Use freely available data from maybe municipality parcel data, USGS maps, Google Maps, and Street View. So moving on to silver. So on pipes, then we're looking at connectivity. Is this pipe connected to the next pipe? Is it connected to the valve, whatever? So also hydraulic grade would be important, expected remaining life, connected services, and asset value. And then for valves, you might want to know the type of valve, the elevation, the open and closed status, and again, remaining life and asset value. And then hydrants and meters, again, very similar type, elevation, life, and value. For pump stations, it can get a bit complicated. We want pump quantity, pump parameters, pump curves, like control information, SCADA availability. For the tanks, you want the type, the elevations, configuration. Is it an elevated tank or regular sandpipe? The shape, SCADA again, and then for reservoirs, sources, type, elevations, and SCADA. So to illustrate that, we're looking at another area here where I've got it themed based on the hydraulic grade. So we're going to zoom in at that intersection there. So we can see that these pink pipes are now a hydraulic grade at 2330. You've got a higher hydraulic grade at 2375 in green. And what's important here is we now know the status of these valves. They are closed, so that's allowing this flow to go this way. It's not allowing the flow to bleed into the 2375, and these valves here are open. So that's very important information to have. We've got elevations on some of these assets. So the fitting here, that's 2144. The valve is about the same. And then we have a hydrant over here at a higher elevation. Okay. And then service connections. You might have that in your mapping. You might have automatically done it. And so what we're looking at here is you've got like this 2330, again, is pink. We've got the service connection here, it makes sense. You've got these green pipes, which are the higher hydraulic grade, and you've got the green 2375 with the correct HDL. But then you've got this one here, which more than likely is really should be green and connected to this pipe. So, mapping that hydraulic grade onto the lateral or the service connections can help with the mapping updates, the asset updates. Control valves, really important. Here's an example here where that 2375 hydraulic grade is actually feeding the 2330 in another location. And we've got a pressure reducing valve here to allow that to happen. Okay. So it's good to note those. And then on the tanks, we had our north elevated tank here before, but now in silver status, we can see here visually, got a photograph of it. It's an elevated tank. We've got the top water elevation. We've got the normal operating level, the lowest operating level, and we'd note that in the GIS, right? And also, the volume of the tank, diameter, that kind of thing. And then similarly on pumps, we just had our one pump station here. But, now we're going to get information on the pump curve. We're going to get information on the control of that, it goes on and off at those levels, and it's controlled by the north tank, another tank. Okay. So the outcome of silver is that the data becomes more useful. We get better understanding of the system. The geometric data is complete. And crucially, the GIS is ready for hydraulic modeling. Okay. And then also from that, financial analysis can be performed. So transitioning from bronze to silver. So if you've got no elevations whatsoever, you could use a topographic ground surface model to populate elevations on valves, hydrants, and meters and fittings. Or you could, now that's good, right? That's a start. But you could also go out and actually do GPS surveys of the valves, hydrants, and meters. That's even better. And then this can be a bit tedious, but talk to your operations people, but you can also get the top water elevations, the SCADA data, location of control valves and pump stations, and to establish the hydraulic rate of the assets. Okay, always good to do that so you know how the system is functioning. Also review the valve open and close status, and then map the service connections to the appropriate mainline pipes. So getting on to gold. And what's common here is the structural and operational condition and history across all asset classes. On pipes, then you want to get maybe the service line material, the manufacturer, and the model or make. Again, valves, model, and make on the valves and hydrants. And then for meters, maybe some other considerations. Again, manufacturer, model, and make, but also maybe the read type. Is it cellular read, AMI, towers, drive-by, whatever. So now service line material, of course, has been really important because of the lead and copper rule. And I think everything had to be submitted initially by October of this year. So a lot of utilities have probably mapped out where their lead lines are. So here we have them color-coded in purple. And you might see here, we've got galvanized iron, HDPE, and then copper colored gold here. So good to know what that is. And then the big stuff. So here we're talking about incident data, inspection data, and intervention data. Okay, this is important information to have on the assets. So incidents, they reflect the health or performance of the system and can help owners prioritize areas to inspect. So the incidents that we typically think of would be pipe break or leak incidents, customer complaints, maybe sinkhole incidents or water quality incidents. So to illustrate that, this symbol here depicts a water leak. So we got leaks here historically. We've got a customer complaint here. There's a sinkhole recorded here and a water quality incident here. Okay. So inspection data, what we're talking about there would be like leak detection, be a big one, valve exercising, GPS surveys, hydrant surveys, which could be, hydrant functionality testing. Does the hydrant even work? And then more detailed hydrant flow testing, where we're seeing the effect of flow on the system. Meter testing, monitoring surveys, where we're recording the pressure at various locations. Pipe samples, like here, or coupons. So we can see the tuberculation, the thickness of the pipe, and water quality samples. So seeing that on our system here, remember we had a break here. So we would probably do leak detection all the way along this area to see what's going on. Are there other additional leaks we don't know about? We've got hydrant tests here. We've got GPS survey, meter tests, pipe sample, that pipe coupon we looked at a minute ago, monitoring surveys, maybe pressure at that hydrant over time, water quality survey, and valve exercising. So another note on inspection data. So leak detection, a lot of different ways you can do that. There is like satellite leak detection, has been around now about, let's say, 7 or 8 years. That can highlight areas where you might want to go actually put some monitors on the ground, like acoustic loggers, put them out in an area, seeing if they pinpoint anything, and then go out there with the ground microphones, correlators, or even tethered inline detectors. And also on hydrants, you can put like remote pressure sensors, so you can record pressure over time. You can have flow sensors, SCADA, connect all those data sources that you may have. And a little note on the hydrant testing. This is an example from an area I looked at a couple of years ago, where we had I think 20 different monitors out there, and we attached them to various hydrants and then went around flowing those hydrants. So we have a hydrant test here, monitoring surveys all the way around. And what we learned is that, for instance, when we flow, this hydrant here, we can see that we're seeing a reaction in this hydrant, but it's not a huge reaction. So we know it's open, but there's bad tuberculation, but there's absolutely no change here. So then we know that this pipe may have a closed valve, or there might be some other constriction, or maybe the pipe was never even connected. But you can do this kind of analysis without even having a hydraulic model. But just something to consider there with the use of hydrant testing data. So inspection data, what's important here is ensure that you've got robust specifications and standard operating procedures. So that, every contractor you have out there collecting data, they're doing it the same way, or even that could be your own staff. And ensure you've got a work order system forms that capture the data you want, especially for decision making. Make sure your inspectors, if they're out there looking at the staff, that they're trained to perform QA/QC on contractor work. And also make sure you got sufficient resources back in the office to update the asset register with the information you've collected. So finally, the other one would be intervention data. And so there we're talking about pipe renewal, which could be, structural replacement, pipe bursting, CAPP, or non-structural, like KELP, which is that, clean, evaluate, line, and protect process for cast iron pipes. You could also have valve renewal, hydrant renewal, meter renewal, flushing, and also know the areas where crews have done restoration for, asphalt, concrete, or, grassed areas. So here we're seeing, again, we knew there was a break here, there's leak detection occurred, and now we're replacing all these pipes. So we'll have pipe repair work orders here, valve maintenance work orders here, hydrant maintenance. And so you've got that record of what's been going on. So the outcome of gold information is that you can mitigate pipe breaks, you can do cost-effective water loss reduction, DMA analysis, district metered area analysis, for water loss, increasing available fire flow, water quality review, and also then creation of a defensible condition-based maintenance program or condition-based renewal program. So transitioning from silver to gold, go out and perform those condition assessment surveys, like the leak detection, valve exercising, hydrant testing, C-factor testing maybe, and update the assets based upon the surveys. You might change some geometric data. You might learn, you thought you had a 8-inch PVC pipe out there. It might turn out to be a 6-inch cast iron pipe. You can add or update condition information, but always ensure that that inspection data is clearly documented and archived, so it's always obtainable. So moving on to platinum then, and platinum, we're really thinking in terms of risk and criticality models and hydraulic models. So on the risk side, you'd want to know about critical facilities, like hospitals, that kind of thing. Cave-ins, sinkholes, road classification, is it on a major highway, or is the pipe under a major highway, or is it on just a cul-de-sac in a residential area? Bus routes, soil classification, population information, employment information, wetlands, water supply sources, and maybe adjacent storm and sanitary systems. Hydraulic model data, you want to go bug your billing people to get the meter demand information in every meter, look at diurnal patterns in the system from flow data. But from there, then you can get pipe capacity, hydraulic rate, fire flow availability, and pressure. So looking at our dummy system here now, we've created a water model of it. And we can see the high pressure here is in the middle of the system, and then we've got low pressure in these areas. So it's very useful having a hydraulic model, highly recommended, highly recommend having all mains models. It makes life so much easier for all decision making. So you can click on a hydrant and see how it behaves over time in extended period simulation. And you can also compare hydraulic model results with actual hydrant test data. So here we've got from a hydrant test at 20 PSI, we're saying 2600. The model fire flow is indicating around 2600. That's really good. We can see here that we got absolutely no flow, no residual pressure, and we're expecting fire flow of 3500. So that'd be one you would go investigate. So always good to compare, like model data with real data collected in the field, for especially in the calibration process. So once you have a model, you can look at existing fire flow. So we can see, so blue is great. I think that's over 1500 gallons a minute in this theme. The red ones are 500 gallons a minute or less, and orange is about 750 to 500. So maybe you're doing a master plan. We're going to extend another pipe all the way along here, add another tank, run that in the model. And now we can see that we've got blue hydrants over here. Still have one red over here, but it's probably a high point in the system. You can immediately see the impact of adding that new connection and tank. So the platinum outcome, it allows hydraulic modeling, risk studies, and we talked about having a defensible optimization program before, which is based on condition, but now you can add the hydraulic and risk parameters to both maintenance and renewal optimization. So transitioning from gold to platinum, build that hydraulic model, obtain data layers from other agencies for the risk, create data layers for critical customers yourselves, establish transparent criteria for scoring assets, and build a risk model. And a risk model, I think we might be doing a future presentation on that. That can be very, very detailed. And then the available tools at the various asset register levels for everything, you'd be considering GIS, aerial imagery, street view applications, topographic ground surface models, decision matrices. But when you get into platinum, you'd be looking for like flow meter data, remote sensors and SCADA, using that quite a bit, and then hydraulic models and risk models. All right, and now on to Phil. I will hand it over to you, sir.
Very good. Thank you, Jim. And first thing I wanted to say, I know Jim has given us a lot of information there, and especially I wanted to speak to anyone who might be down at the beginning stages of this. And I just want to say, it's really important that you don't let all of this intimidate you. Don't let what looks like a really enormous thing, don't let that overwhelm you. There's going to be steps that you can take that can get you moving in the right direction. So it's important to really understand where you are, even if you're starting with nothing, or if you're up near the platinum end. And then you need to educate your colleagues and the management staff on the benefits of what this is going to do for them. Establish your goals so that you can constantly be improving your asset register. Develop some plans to advance to the next level wherever you are. And then it's going to be really important to get out there and advocate for some additional funding, that you need to have sufficient funding. None of this gets done for free. And you want to also have the resources that you need to meet those goals. Then you constantly want to be measuring the performance of the staff assigned to meet these goals. And as I was saying about not getting, letting the enormity overwhelm you, don't get wrapped around the axle with this stuff, and don't let perfection become the enemy of the good. And I would say too, just remember, we've shown you some different levels here from bronze to platinum, but our levels, they're not set in stone. Every utility is going to have a mixture of things. So some are going to have models without being what you call full platinum. Some are going to have risk models with just some bronze data in it. So they'll still be able to do it. It just won't be quite as complete as if it was all platinum data. Okay, next slide, please. So here we have some materials, and some of these pipe materials are going to be very obvious as to what they are. If you're looking at HDPE pipe, that's going to be black pipe, blue stripe on it. If you're looking at PVC pipe or ductile iron, all of those are going to be readily evident as to what they are. When you start looking at some cast iron, if you're looking at pit cast or spun cast, you're probably going to need to have a section of that, or at the very least a coupon. So just remember that. All right, next slide, please. Okay. So if you don't have plans from the original installation of this, there are other ways you can use to get your approximate age on an asset. So if you got building or tax records and they show when a building was built, you can use that. So if you use the recorded date of a subdivision, if that's what you've got, when that was platted, that's all you have, use it. And you can infer diameters and materials from adjacent assets. You've got two places where you went out and done interventions, and there's a section of pipe in between it. The two outer ones are the same material and the same size. What's in between is probably going to be that. So you can just need to remember that this is going from nothing to something. So if you've got a date that's really off by 10 years, or if your pipe diameter isn't quite right, if it's really an 8-inch line instead of a 12, you can correct that when more accurate information is collected. So just remember, this is a starting point. All right, next slide, please. And then transitioning from bronze to silver. So if you got your pipe material, you can estimate a life expectancy for the asset. Your life expectancy is going to vary depending on the age and your material. And you can always go talk to your finance department and they can help you with depreciation information. And that's going to be a good start for some of these. But once you have your life expectancy and you have your approximate age of the pipe, then you've got your remaining life. And of course, now the present condition of the pipe is going to have a huge impact on that remaining life. So that's a really big consideration. So try and use that if at all possible. But if you only have the material type and the age, you can come up with something and use that kind of as a last resort. All right, next slide, please. All right, so talking about intervention data, I really can't overemphasize how important it is to train your dig crews to record as much information as possible. There's going to be times when you run into resistance on this, and they're not going to want to do it. But when you've got that pipe opened up, there's just so much good information that you can get that you've got to get it recorded. So train your crews to verify the diameter and pipe material. Get them to take photographs of it. But you can also have them bring back a section of the pipe or a coupon so you can assess deterioration and tuberculation. Have them also verify and record the bedding conditions. That's something that's extremely important too. It's going to help you predict additional issues. And if there's any evidence of corrosive soils, get them to take some soil samples, send those off and have them tested. DIPRA, that's Ductile Iron Pipe Research Association. It's just an excellent resource for that. They're always willing to help. For valve and hydrant repairs or exercising and routine maintenance, those are also really important to provide data so that you can compare that to your GIS information. And one thing I'll say, a helpful strategy if you need to develop your work order sheets with highlighted fields in them, if you've got digital ones, and make it to where those are mandatory fields, that they have to enter that information, such as diameter, or pipe material, the depth. If you do that, make those mandatory fields so they have to be populated before someone can complete that work order. And it helps people if they're just a little forgetful about it. So that's extremely helpful. All right, next slide, please. All right, talking about water quality. So in tanks and out in the distribution system, your water age is going to be a really big factor with water quality. And we do consider that to be in the gold level. So things like mixers in tanks and your average water age. If you've got test results for you've done your DBP testing, you also might have records on your chlorine residuals out in the system. And there might even be some areas where you have to add chlorine if your residuals aren't staying up high enough. So in the distribution system, your pipe flushing, either whether it's automated or if you're doing it manually on a set schedule, that will help with your DVPs and with your chlorine residual. And if you've got a unidirectional flushing program, that's going to push your sediment and mineral buildup, going to push it away from the treatment plant, push it out of the system. So that's all information you could be putting in there. Next slide, please. All right, now we get into the platinum data, and we're talking about some criticality here. So here we got a couple examples, and in all honesty, they're probably at two extremes as far as criticality goes. So if you look at these two, the first one, pipes in front of a hospital on a major road, crossing a railroad, you got a 10-story apartment complex. That's clearly a very critical line. And if you look at the second example, it's water piped into a cul-de-sac, single-family residential neighborhood. You only have 4 houses connected. There's not been any previous repairs, and you've got plenty of fire flow and no pressure issues. That one's far less critical than the other. And with those two, you look at those and everybody goes, that's common sense. But we're going to look at how you can quantify that. So next slide, please. Okay, so the two things that we break the risk and criticality down into are consequence of failure and likelihood of failure. So the consequence of failure, you look at locations where failure would result in high risk to critical facilities, communities, and businesses. And then on your likelihood of failure, assets that have exhibited operational or structural issues. If you've been having problems with these lines in the past, chances are you're going to continue to. So your likelihood is much higher. And in your risk, you can just take your consequence of failure, multiply that by your likelihood of failure for each asset, and there you have your risk. So next slide, please. All right. So you can customize your consequence of failure and your likelihood of failure scores, kind of fit your own individual situations. But we've got some reasonable scoring criteria here. And you might say that the pipe A, it's adjacent to a hospital, so it gets a score of 10 on the consequence. Pipe B, it's adjacent to a school, so it gets a 6. Pipe C, it's adjacent to single family homes, so it gets 2. And then your likelihood of failure, you've got a pipe with no issues recorded, that scores a 1. It's got a few issues, scores a 4, and a pipe with multiple issues scores a 10. So just remember, you can make this as exhaustive or as simple as you want to. So just try and strike a balance between enhanced detail and ease of use, because as you get more detail in there, it becomes a little more cumbersome. So there's going to be a balancing act somewhere. All right, next slide, please. And next, we've got how we go through and calculate the risk. And as you can see, the end result of what we've created here, it's a data-driven plan for your corrective maintenance capital program. So once you have those individual pipes evaluated for risk and criticality, you can take those individual pipes and then you can aggregate that over the entire area, over a pressure zone, whatever, to prioritize your work. And collecting the data, analyzing the data, and using the data, along with the assigned risk factors, it provides you with a good defensible plan, and you can use that to address your capital replacement needs. If you look at the little matrix we have here, we've got consequence on the one side and probability on the bottom. You get down into the lower left, and that's where you've got low consequence and low probability. You fix that when it fails. Up at the opposite end of the spectrum, where you have high consequence and high probability, that's fixed now. And in between, you've got fix soon, or schedule a renewal, or just monitor it. So that's what you end up with when you're looking at this risk and criticality. So next slide, please. All right, so while the previous slide it was pretty generic and rather simple. So here you can see how it can become a lot more detailed. So this example comes from a utility with over 3,000 miles of water mains. And if you look at this, the high-risk pipes are shown in red. And it's still got the same type of matrix on it, still using the same thing. So this gives you a little idea of how you can apply the simple concepts to a much larger system. Okay, next slide, please. Right, now we wanted to talk about and touch on some considerations for different eras or cohorts of pipe. So we've got a couple of different cast irons there. The first we're talking about is pit cast iron, and that became common around 1865, but up until about turn of the century, 1901, there was no accepted standard with that. So in 1902, there was an AWWA standard adopted. And if you're looking at pit cast pipe, it's typically got thicker walls, and it can even have, if they got the bore off center when they were casting it, you could even have one side of the pipe, the wall thickness be a little more than the other. So that's one defining characteristic whenever you're looking at a section or a coupon out of that. And then spun cast iron, started seeing that around 1922. Again, there was no AWWA standard until after 1938. But now this has a thinner wall. And then from 1939 to 1948, you had an AWWA standard, and a lot of times you'll see lead service lines there with that. They were widely used with spun cast iron there. And then whenever you get up into 1949 to 1975-ish, you start seeing the spun cast iron, and you'll see copper services. And because you might get some galvanic reaction there between those dissimilar metals, this is one cohort we say it's very susceptible to corrosion. And then the last one we've got on this slide, talking about galvanized iron, you're again talking about a lot of corrosion. And if you find something that is galvanized today, you're typically going to find something that's in an extremely corroded state. All right, next slide, please. Then moving on to some more recent years, we've got the most common pipe materials are ductile iron and PVC. So from 65 to 1990, the ductile iron pipe was produced under the first AWWA standard, and that was thickness class pipes. And you see class 50, 51, 52, 54, that's your thickness class pipe. And now that pipe, it had some corrosion protection, the exterior coating, it had an interior cement lining. Then in 1991, you got the new pressure class standard from AWWA. So when you talk about 350 class, that's the newer stuff. So you can still get both today. The pressure class is probably gaining a little more popularity maybe. But then talk about PVC pipe. So from 1969 to 1975, that's what's commonly referred to as the ASTM series. And then PVC from 76 to 97, that was C900, which is still around today. You still buy C900 pipe today, still use it. But then in 1998, we started getting we got the C909 standard, and that was adopted for what they call molecularly oriented PVC. So that's, gives you a thinner wall, same strength or even better strength sometimes. So that's what you see there. Next slide, please. Now let's talk a little bit about some project creation and optimization. So now you're pulling together the data that you've been collecting. You've considered your high-risk pipes. You've been looking at clusters of breaks or other issues, and you start thinking about the breaks per mile of different pipe cohorts. Then you use your hydraulic model or your flow testing to identify areas that have less than what the prescribed fire flow is. And lastly, you try to determine what is optimal project cost for your local contractors. So you see what we've got here. We say as an example, say you find that the contractors in your area, they've got an optimum project cost of around $1 million. And maybe that's where their bonding limit is on that. So what you want to do is try and create projects that are around $1 million. And we're saying that's probably about a mile of 8-inch pipe, or maybe it's a half a mile of 12-inch pipe. And that's going to depend on where you're putting it, what kind of ground conditions you have. There's a lot of things that are going to happen there. But the point is that if you're excluding contractors because they simply can't handle the size of your project, then you're going to see higher costs. You're going to see inflated costs on these things. And that's going to reduce the amount of work that you can ultimately accomplish. And that's what we're after here in the end, is to be able to get out there and replace as much of this as we can. So that's something very important to keep in mind. Next slide, please. All right, so here we've got a map that's showing some of our data area here, and you can see that we've got an area kind of in the upper portion of it where we've got a cluster of breaks, and we have identified that as a replacement project. So you see the dashed heavy red line. That's the replacement project that we've identified here that we're going to try and get done. Okay, next slide, please. And we're going to cover a few other items here. This is the last slide, and what we wanted to talk about, that your pipe joint material, you really ought to consider that too. So if you've got leadite there, if you got some cast iron pipe and you have leadite joints rather than pure lead, you're going to find that those can be much more problematic, and what we're seeing is about 5 times more likely to cause a premature joint failure. So for iron pipes, I know I mentioned earlier about the galvanic reaction, so consider the galvanic effect and maybe some corrosion protection. You need to be thinking about your pressure data, if both constant pressure and data spikes that you might see out there. All of that's extremely important. And we mentioned just a little bit earlier on the interventions, when you're talking about soil characteristics, you need to consider that too. So you see this photo over on the side. That's a piece of ductile iron pipe, and it was only in the ground for about 20 years. And from what it looks like a bucket tooth probably gouged the pipe, and then the corrosive soil that it was in did the rest. So the pipe was installed near an old foundry, and when they dug through, the adjacent soil showed multiple distinct strata on this. So when that was done, they did take samples from each stratum and they sent that off to DIPRA. I mentioned doing that earlier, and DIPRA came back and they confirmed that some of the layers were quite corrosive, some of them weren't. So that's something that you definitely want to take into account. And then the last thing that I'm going to mention is that you really want to hold on to your replaced pipeline data and your inspections. So you're getting a lot of information there. You don't want to lose that. So keep that, hang on to it. Don't let someone delete that. So that was the last slide, as I said, and I will turn it back over to Rihanna.
Thank you very much, Phil, and thank you, Jim, as well, for the amazing presentation. We'll now be opening up the Q&A portion. Again, attendees are welcome to type their questions in the chat, type in the Q&A section, or raise their hand. I see that we already have one question from Mark Wolcott. I believe that's how you pronounce that. The question is, do you have experience using 3D GPR for mapping from a mobile unit passing over the pipe system from the roadway to present the extent of moisture around and along leaking assets for extent of leaking?
Okay, I'll take that one. So I don't have direct experience with that, but I've seen some presentations on it. But yeah, it would be an interesting approach to see how effective that would be. I don't know, Phil, do you have any thoughts on that?
Yeah, I really haven't used that either. So I really can't speak to how well it would work, but it certainly is interesting.
Okay, awesome. Thank you both for answering that. Are there any other questions? I will give, we got a thank you from Mark. You're welcome, Mark. Oh, we have another question. This one, it says, is there any frameworks or codes to detect existing pipes? And how do you get the details or parameters of those pipes?
Sorry, could you repeat that?
Yeah.
Yeah, so the question is from an anonymous attendee. It says, are there any frameworks or codes to detect existing pipes? And how do you get the details or parameters of those pipes?
I don't know if codes necessarily like one would have with NASCO, but for on the source side. But I would say it's not that complicated. I mean, like Phil showed a little cheat sheet there on the materials. So, there's going to be, 7 or 8 different materials that you would typically encounter. And it's, I would say, if you just start looking up spun cast, ductile iron, lead pipes, HDPE for water, whatever, you would quickly find some images. And what I'd recommend is take if you are trying to collect data on that, maybe create a PowerPoint with just the various pipe types and just add some images to all of them, so that if you're trying to educate yourself and your staff, that you've got a common reference that you're all in agreement on. But yeah, so Phil, anything to add there?
No, I think your advice on getting something with a common reference for your staff to use, I think that's an excellent idea.
Okay, that's great. Thank you both for answering that. Hopefully that answers our question. Are there any other questions that we have? I'll give it a minute just to make sure I'm not missing anything.
And while we're waiting for a second, I'll just make one other comment that I probably should have made earlier. That we showed we showed a bunch of images there from various different software packages, to illustrate the the asset register data that's available. But all utilities manage data different ways. Some people might use products from like Esri, and they might have other asset data linked in other tables to other work order systems and that kind of thing. Other ones might use like Info Asset Manager or something from Autodesk. There's lots of different products out there, like Lucity or whatever, Cartograph, where people could be storing the data, right? But the important thing is to have a unique identifier, and that's used across all different software products. But it's referring back to that the source of truth would be the GIS with the unique identifiers where they're defined. So that's just one addition I wanted to make to the presentation here.
Thank you for adding that detail. Note to self, the source of truth is GIS.
Yep.
Okay, thank you. We did have one more question. Oh, we had a couple more questions come in, actually.
What have I started? Okay.
So the first one we have is from Michael O'Shea. This question is, Do you have any recommendations for best practices regarding building attributes into asset data versus what types of data to manage in related tables or other databases?
I'd say for building data, the big thing would just be the age of the building, like when it was, or the year built, whatever. That's the primary one I've used, just to take that from the building, transfer it to the parcel if it's not already connected, and then from the parcel to the service line, and put that age of so if it's like, you know 1939, it's more than likely lead, right? So but then also transfer that age potentially back to the water main as well. But that's the big one I would use. The other one I would use would be, and this is maybe where you're pulling data in from your billing system, is is that customer or that property an active user, or has the property been abandoned? So that can be very important if you find out that the property's been abandoned, but and the water service has been cut and it's been leaking into a basement or something for 20 years. So it wouldn't be a good thing. So Phil, any thoughts there
Well,
too?
I guess I was taking his question as being a little different. I thought he was asking whether you want to build the attributes into the asset data, or do you want to try and put it in related tables and have it linked to that? So I took his question to be different.
Oh, okay, go on. Okay.
So, and it's really a question. I don't know the answer to which of those is better. You've done more of the actual nuts and bolts of setting up this, Jim. So what would you say on that? Do you have an
Could
opinion?
be done either way. I mean, there's a couple of ways you could do it, just by, having some sort of an API with that other system, so that you're just pulling that data directly into your asset management or GIS system. But it would probably depend on the software involved. And Michael, I know that you're a fan of that Esri product, aren't you?
If it helps, Michael did come in saying that Phil's interpretation of the question was correct, and yes, he is a fan of that Esri product.
Okay. Yeah, I've known Michael for years. Yes. So, yeah.
Oh, this is funny. Okay. Thank you both for addressing that. I'm sure Michael appreciates it. So the next question we have is from Vinesh. His question is, how are the pipe laying approvals happening currently? Are there any practices followed in the US like BIM models or georeference files?
Bill, do you want to take that one? You're probably more closer to the construction end of things than I am these days.
Yeah, we have our current standards that we follow, and we've developed those over the years. And so we go through the approval process. If a developer or someone is installing pipe anywhere, we have a couple of crews that do capital projects ourselves, going out and replacing what we call substandard water lines, where they're generally either undersized or we've had problems with them when they make it onto the list. Going through some of these things, those are the ones that we do ourselves. So we follow our own book of standards that are for Augusta Water. I don't know about the BIM models or georeferencing any files. So we've developed our own standards for what we require as far as pipe laying, and all of the work has to conform to those standards.
Thank you, Phil.
Perhaps it might be more in use in very urban areas. I could see that being the case. So whether you've got lots of utilities. Yeah.
Okay. thank you both for addressing that. Hopefully, Vinesh, that answers your question. And just going to check to see, do we have any other questions? I'll give it a moment. I know that typing can take a while.
And we don't want any hard questions because Christmas is around the corner, you know.
We don't want any hard questions.
Yeah.
Hard questions get coal in the stocking.
Mm-hmm.
You two are Santa now. Okay. All right. I don't think there are any other questions coming in, but I take it that you both are open to people reaching out to you if they have questions they think of.
Sure, absolutely.
Absolutely.
Awesome. Okay. In that case, the only other comment that we have is from Michael again, who says, thanks, Jim and Phil. Great presentation. Mark also says, we'll email you the hard ones.
Oh no, oh no. Okay. Phil will be taking them. Yes.
Phil will be taking all of the hard questions,
Yes.
everyone.
Yeah, and I'm going on vacation tomorrow, so.
Yeah, he's apparently listening to the questions, unlike me.
You are so funny. Okay. At any rate, that concludes today's webinar. We will definitely be sure to have more in the future, so make sure that you're following UESI on all socials. Thank you all for attending and have a happy holidays.
Thank you very much. You
Take
too.
care. Bye-bye.
Merry Christmas, happy holidays.